If we have a bulb connected to a bunch of wires, the question that we're going to answer in this video is how do we set up a current in these wires? And we'll also learn what a battery does and what does voltage really mean. And to do all of this, let's start by thinking of an analogy. And the analogy is this picture of happy kids playing on a slide. If, as the kids slide down, someone could pick them up and put them back at the top continuously, then I'm pretty sure you can guess there will be a continuous motion of these kids. And so there will be a continuous current of kids. And so we'll keep this picture in our mind as we try and understand how to produce a continuous current of charges. So let's start looking at this a little deeper. If you look at the kids who are on the slide, what's making them move from here to here? I'm pretty sure you know the answer to this. It's gravity. Gravity is the one that's pushing them down the slide. In a similar manner, there are charges present everywhere in the wire already. We have already seen that these wires are all metals, and metals have loads of electrons, which are negatively charged particles, free to move inside of them. The only problem is they are not moving, they are at rest. So to make them move, we need to push them. Just like how gravity pushes these kids, we need an electric force to push these electrons. And that electric push is what is given by a battery. So of course, there are charges inside a battery as well. But what's important is that one side of the battery is positive, the other side is negative. That starts pushing these electrons. Now, for simplicity, what we will do is we'll assume that these are not negative electrons, but we'll assume them to be some kind of positive charge. The only reason being, the direction of the current is the direction in which positive charges move. That's how we chose the convention, isn't it? So thinking in terms of electrons might be slightly annoying. So we can focus more on the concept over here easily if we just assume that these are positive charges, all right? So if we think of them as positive charges, we can now see the positive terminal of the battery pushes these charges away from them, and the negative terminal of the battery pulls these charges towards it. And as a result, we now have an electric current motion of charges in this direction. And just like over here, for continuous motion of the kids, someone needs to continuously keep picking these kids up and putting them back over here, pushing them against gravity. Over here, someone needs to keep picking up these charges and push them back up continuously against the electric force. And that job is done by the chemicals inside the battery. There are some chemical reactions that go on, and these chemical reactions start pushing these charges up against the electric force, and as a result, we have a continuous motion of charges, creating a continuous supply of electric current. And if you could see those charges moving, it might look somewhat like this. That's it, a very brief animation. Now, to understand what voltage is, let's come back over here. As these kids move down from more height to less height, they gain energy. If this was a very smooth slide, they might have gained kinetic energy. They might speed up. But if this was a rough slide, let's say, then because of the friction between their body and the slide, then there is a lot of heat generated. So as the kid keeps moving down, there is a lot of heat generated in the slide. And since heat is a form of energy, we could ask, where did that energy come from? And you may already know the answer to this. We say that energy was already stored up in this kid. As the kid moved down, slowly, the stored up energy got converted to heat. And this stored up energy is what we call potential energy. And so every kid at this point, topmost point of the slide, has very high potential energy. And so we could say this point is high potential point, high potential. And as they move down, they lose potential energy and convert into heat. And by the time they come over here, they would have lost all that potential energy. So we can say this is low potential point, low potential. And as the kids move back up, they gain potential energy. And who gives them that potential energy? Well, again, you might guess it's this person who's pushing them up. He's the one who's transferring the potential energy back into the kids. And again, the kids lose that potential energy, and so the cycle repeats. In a similar manner, as the charges move through the bulb, there is heat generated in the bulb. Again, we could ask, where did this heat come from? In a similar manner, we could say the charges over here might already have stored energy. And as they move through the bulb, they lose that stored energy. And so we can say that the charges over here have high potential energy, and the charges over here, as they move down, they lose, so they have low potential energy. The only difference between these two cases, one is that this is due to gravity, this is due to electricity. But another major difference you can see is that over here, as kids are moving down, they are continuously losing potential energy and producing heat. But over here, we are going to assume that not much heat is created in the wires. I mean, you know that in reality, the wires do get hot, but they don't get as hot as the bulb, isn't it? So to keep things simple, we like to assume in all the circuits that we deal with that there is absolutely no heat generated in the wire. And so that means that the charges don't lose any potential energy up till this point. Then they lose all the potential energy, gets converted to heat, and then they come back. And so in this case, we can now say that all the charges over here in this section of the wire have high potential energy. So this is high potential point. And all the charges over here, they have lost their potential energy. And again, they have the same energy because they don't lose energy to the wire. In reality, they do, but we are assuming they won't. And so we can say all these charges over here are at low potential. So every time charge moves through the bulb, they lose potential energy. And every time the chemicals in the battery push them back up, they gain potential energy. That energy comes from the chemicals of the battery. Just like how over here, the energy comes from this guy. And voltage is simply the difference in the potential energy of the charges. And that's why voltage is more technically called just potential difference. It just tells us what's the difference in the potential energy of charges. So for example, we'll take an example and understand voltage. For example, over here, if we said the potential difference between these 2 points is 1.5 volts, then it means there is a difference in energy, potential energy, of 1.5 joules per coulomb. The per coulomb part says that every coulomb as it moves from here to here, it gains 1.5 joules of potential energy. And similarly, when a coulomb moves from here to here, it loses 1.5 joules of potential energy and gets converted to heat. So voltage just indicates how much potential energy a coulomb gains or loses. If this was a 9-volt battery, then every coulomb gains 9 joules of potential energy as it comes here. And per coulomb, it would lose 9 joules of potential energy as it goes from here to here. So there will be more heat generated per coulomb. That's what a 9-volt battery would do. And this number also means that if there were 2 coulombs that go from here to here, then they would lose a total of 3 joules of potential energy, 2 times this number. If there are 10 coulombs that move from here to here, they would lose a total of 10 times this number, 15 joules of potential energy, and so on. So knowing the voltage helps us calculate how much potential energy would be lost or gained when charges move from one point to another. Also, if we were to take these 2 points in the circuit, then the potential difference between them is 0. Can you understand why? Pause the video and think about it. Well, that's because we assume that there is no loss in potential energy as charges move through this wire, and therefore the potential difference between these 2 points is 0. Similarly, I hope you agree, potential difference between these 2 points is also 0. There's only a potential difference between these 2 points, and since this is at a high potential, we tend to put a plus sign for high potential and negative sign for low potential. And similarly, there's a potential difference between these 2 points. And therefore, we always say we can get a continuous supply of current if we maintain a potential difference between ends of the wire. All right, one last thing is, in some textbooks, they define voltage in terms of work done. It's pretty much the same thing. So let's just look at what that is. You see over here, when the battery is transferring the charges from low potential to high potential, we saw it's the battery who's transferring energy into the charges, just like how this guy transfers energy into the kid. In physics, whenever you transfer energy, we say you are doing work. That's it. So over here, we can say the battery is doing 1.5 joules of work per coulomb that it transfers, right? And so from this, we can now say voltage also tells us how much work is being done. Work is being done in transferring charges from one point to another per coulomb. Per coulomb. That's it. So to summarize what we learned, we saw that in order to maintain an electric current in a circuit, we need to maintain a potential difference. The potential difference, or voltage, is simply an indicator of how much potential energy is gained or lost per coulomb when it moves from one point to another. It can also be thought of as how much work needs to be done to transfer the potential energy per coulomb from one point to another.